Hello, this is going to be my first of 3 videos on volume as it appears in AP Calculus. This one will be volume with the disk technique, where we're rotating a region around an axis. I'll come back with another video, volume using the washer technique. Okay, that's a little more complex. It's going to be volumes where we're revolving around an axis, but there's going to be some sort of gap in the middle. And then I'll also come back with a video on volume of solids with known cross sections. And those are really the 3 volume techniques that we need to be able to do in AP Calculus. I also want to just remind you that the shell technique, while a great technique for finding volume, is not something that's included in the AP Calculus course anymore, so I won't be doing a video on volume with the shell method until probably the end of the course. It is one of those topics, though, that, if you find yourself in a Cal 2 class at a large university, they're probably going to expect that you've taken volume with shells before. So I'll show you how to do that, but probably after the exam. Okay, so the first example I'm going to give you is really probably one of the first examples you're going to see in any Cal 1 course. We're going to start by rotating the graph of y equals square root x around the x-axis to form a solid. Okay, so you can think that that's going to look kind of like, I don't know how to describe it. Let me try to draw it for you. Like a gumdrop or something like that. And what we're going to do is we're going to rotate this around the x-axis to form a solid. So you're going to have to, kind of just envision that. Maybe I will come through, though, with kind of the bottom half of it in gray. It's going to end up there. It's probably not a very good picture. But I'm going to then kind of give it some depth here. I'm actually going to remove the x-axis for a second. I'm going to say that we revolved it, so it's going to that. I cut through it. And I might actually give this some thickness, because when we go to find the volume, it's all going to go back to the idea of the Riemann sum. Just like with area, just like with arc length, just like with any of the things that you're going to see in this unit, it all goes back to the idea of the Riemann sum. So here's the x-axis. I'm going to kind of stop there and then maybe pick it back up here to give it some depth. And there we go. Okay. So that is one of our disks. And now, kind of the hallmark of the disk technique, I forgot to mention earlier, is that the region that we're rotating around, around the x-axis, is going to be touching the region that's getting revolved at all times. Okay? If the region all of a sudden is not touching the axis of rotation, that's going to require a different technique. That will require the washer technique. Watch part 2 of these 3 videos to get more information on the washer technique. I've got a lot of examples on that one. For now, we're just worrying about the easy ones. Okay, we're just going to rotate r around the x-axis. Okay, maybe later I will rotate r around the line x equals 16, and we can look at what that would look like as well. Okay, find the volume of the solid. Okay, well, the volume of the solid is going to go back to adding up a bunch of these disks. And now, kind of, let me just pull this disk out and turn it on its side. That'd be probably the easiest way to go. Maybe I'll even still give you let's see, here's the x-axis coming out. That's the x-axis that we're revolving around. I've turned it sideways just to make it easier to look at. Okay, so if I wanted to find the volume of this small disk, well, this is some type of prism, and so it's going to have some radius, some height. Okay, if we go back and look over here on the x-axis, the height is pretty much going to be just delta x, right? It's the really small disks. The disks are going to get smaller and smaller, and the number of them is going to go towards infinity, so that we can get an integral and actually, use calculus to find these volumes. All right, so we're going to be eventually getting volume by adding up a bunch of disks. Okay, so the area of the face of the disk is pi r squared, and the height of the disk is delta x. As I said, the number of disks goes towards infinity, and the width of each disk goes towards 0. This will become the integral of pi r squared dx. Okay, now when we go and revolve around a vertical axis, this will become pi r squared dy, because the thickness of each disk will be delta y, and that whole rigmarole. So we've got ourselves a technique for finding volume. We need a radius, though. Okay, so let me just say that the radius, here, maybe I'll kind of color over this in blue. This radius is going to be here. Now, this integral needs to be in terms of x, so I'd like for the radius to be in terms of x as well. And we can see if we do top minus bottom like we did with the area stuff, the radius is going to be equal to top minus bottom, y equals square root x minus y equals 0. Okay, so that's just y equals square root x. Okay, so the volume is equal to the integral of pi times r squared root x, dx, as these disks run from x equals 0 up to x equals 16. I'm going to factor out the pi in front. I'll multiply by pi at the very end. 0 to 16 of x dx, which is going to be pi times 1/2 x squared from 0 to 16. And maybe 16 was a little bit ambitious because I'm going to have to go over here, and I'm pretty sure 16 squared is 256, but I'm just checking to make sure on a calculator. Yeah, it's 256. Okay, so this is pi times 256 divided by 2 is 128. I can do 0 squared divided by 2. That's going to be 0. And so this is going to be 128 pi. Next, I've got this region G, which is enclosed by the y-axis, the graph of y equals e to the x, and the graph of y equals 10. I'm rotating around the y-axis to form a solid, and I want to find its volume. Okay, again, I'm seeing that the axis of rotation is the y-axis, and the y-axis is touching the region at all points. Okay, so this is going to use the disk technique. So I'm going to say that I know that volume is equal to the integral of pi r squared for disks. Okay, this is going to be with respect to y because each of these disks is going to be sitting horizontally, and they're going to slide up and down the y-axis from y equals, well, whatever this intersection point is here, that's going to be 1 because e to the 0 is 1, up to y equals 10. So 1 to 10. I'm going to need to write down a formula for r, though. Okay, so r is going to be right minus left, and x equals something minus an x equals something else. Okay, well, and I don't have x equals for this curve. If y equals e to the x, then x is equal to the log of y. Okay, so right minus left is x equals log y minus x equals 0. The y-axis is the line x equals 0. Okay, so that's just r equals the log of y. Okay, so I'm going to factor out the pi. I've got the integral from 1 to 10 of r squared is the log of y squared dy. And now, okay, the problem is that y'all don't know an antiderivative for log yet. You certainly don't know an antiderivative for the log of y squared. So this is the type of problem that's either going to be use the calculator to find the volume, or set it up but don't evaluate. Okay, both of those things I'm pretty confident y'all can do, so I'm just going to kind of stop here. That's an integral that represents the volume of the solid generated by rotating G around the y-axis. Okay, now I'm going to go back to the other region, this region R. Not sure what happened to R, I must have erased it. Is rotated around the line x equals 16 to form a solid. Okay, well, there's the axis of rotation. See, it's touching the region everywhere. And, okay, we're forming a solid. Find the volume of the solid. Okay, we can do that. So the radius of this thing, I'm going to use the disk technique. Okay, the radius reaches from the axis all the way to the curve. So in this case, the radius is going to be, and this, what you want to do is just live with top minus bottom and right minus left. Don't think about this too hard, okay? Remember, this radius needs to be positive. So we need right minus left to make sure that it's positive. So right is x equals 16, and left is x equals, well, we don't have x equals. We have y equals the square root of x. So if I squared both sides, I would say x equals y squared. Okay, so right is x equals 16, left is x equals y squared. Okay, so I've got myself a radius. I know that for these disk method volumes, the volume is equal to the integral of pi r squared. Okay, since we're rotating around a vertical axis, these disks are going to slide up and down, so I need to integrate with respect to y. And that's going to go from y equals 0 up to y equals the square root of 16. Okay. And I'm going to factor out the pi. I know what r is. R is 16 minus y squared. Okay, I got to square r, integrate with respect to y. And again, this is the type of thing that you could do, especially if you squared out that integrand. Use the power rule, plugged in top and bottom, subtracted, multiplied by pi. I think that that's the type of thing. If you need practice with that, you should go ahead and do it. But I'm not going to, for the sake of time. I'll keep this video short. The last one I've got for you is going back over to that other example, y equals e to the x, y equals 10, the y-axis, enclosing g. Where now we're going to rotate g around the line y equals 10. Okay, so again, the axis of rotation is entirely touching our region. Okay, so it'll be a nice solid object with no gaps or holes or anything in it. And we're going to form a solid. Okay, so I'm going to use the disk technique. And so I'm going to need a radius. And again, you want to go top minus bottom. Okay, so in this case, the radius is going to be top is 10 minus the bottom is e to the x. Y equals 10 minus y equals e to the x. Okay, now we're going to find the volume. We know that with disks, volume is equal to the integral of pi r squared. Okay, these representative rectangles or slices or whatever are sitting vertically, or they run along a horizontal axis, however you want to think about it. So I'm going to need to integrate with respect to x. And we're going to go from x equals 0 to, oh, this is interesting. Okay, well, we need to know what x is when y equals 10 right here. Okay, well, y equals 10, so 10 equals e to the x. I'm going to take the log of both sides. So log of 10 is the log of e to the x, which is just x. It's okay. Well, that's something nice. Okay, log of 10, just a number, nothing to be scared of. Okay. And I'm going to factor out the pi, substitute on r, still integrating from 0 to the log of 10. R is 10 minus e to the x. Square r, integrate with respect to x. And that's the type of job I think, well, probably you actually don't need a calculator for, but it's, not going to be a real nice number. So I would let you do that on your own. That's going to be all I've got for you on the disk method. Okay, for more examples on volume, watch the washer video, watch the cross-section video. There's lots of examples. Do quiz 8.2. That's a pretty beefy quiz. That'll be a really good set of practice problems for you if you haven't already done those. And don't forget about ArcLink.